So this is going to be over section 26.3, interference in thin films. So when you have light that's reflected from both sides of a thin film with thickness T, which you can see the diagram down here below, you've got air coming in, you've got the film, and then you've got some sort of index associated with it and has a thickness of T. You've got the rays coming in here, striking that, coming into the eye, and then it goes down a little bit and then comes back up and gets refracted again. And then you can see where it's being focused on the retina of the eye. So when light is reflected from both sides of a thin film with thickness T, then constructive interference between the reflected waves occurs when this happens. Unless a half cycle phase shift occurs at only one surface, then this is the condition for destructive interference. A half cycle phase shift occurs during reflection when the index of refraction of the second material is greater than that of the first. So you often see bright bands of colors when light reflects from a soap bubble or from a thin layer of oil floating on water. These bands are going to be the result of interference effects. So light waves are reflected from opposite surfaces of thin films, just like you saw in the summary. In constructive interference between the two reflected waves, a different path lengths occurs in different places for different wavelengths. So the situation is going to be shown here in 26.8a. So you've got light reflected from the upper and lower surfaces comes together at the eye at point P, undergoes interference. Some colors interfere constructively and others destructively, creating that iridescent color bands that we see. So light shining on the upper surface of the film with thickness T is partly reflected at the upper surface. Light transmitted at the upper surface is partly reflected at the lower. The two reflected waves come together at point P, and depending on the phase relationship, the wave may interfere constructively or destructively. And different colors have different wavelengths, so the interference may be constructive for some and destructive for others. And that's why you see the reflection as you do. So here's a situation involving monochromatic light that reflected from two nearby parallel surfaces and nearly normal incidence. Figure 26.9 is going to show two plates of glass separated by some distance there, h. Reflections also occur at the top surface of the upper plate and the bottom surface of the lower plate to keep our discussion simple. The situation is the same in 26.8a, except that the path length difference is due to the air wedge instead of the film. The path difference between the two waves is just twice the thickness T of the air wedge at each point. At points where 2T is an integral of the number of wavelengths, we expect to see constructive interference and a bright area. Where this is a half integral number of wavelengths, we expect to see destructive interference in a dark area. Along the line where the plates are in contact, there's practically no path difference and we expect a bright area. So when NB is greater than NA, we will have no phase shift occurring. When NB is greater than A, we will have a half cycle shift going on. So you can see here a summary of the thin film interferences. Newton's rings. This right here can end up producing circular interference fringes. It's a convex surface of a lens in contact with a plate glass, plain glass plate. A thin film of air is formed between the two surfaces. When you view the setup with monochromatic light, you can see circular interference rings, first studied by Newton. And when viewed by reflected light, the center of the pattern is black. And can you see why a black center should be expected? Yeah. So there's some neat things out of this particular section. Um, Again, you can see your non-reflective coatings for lenses, for lens surfaces, make use of thin film interference, a thin film of hard transparent material with an index of refraction smaller than that of a lens material. In other words, you've got the index of refraction out here, which is less than what you see in the film, which is less than what you see in the glass. This is considered to be non-reflecting film. The destructive interference occurs when the film is about 1/4 of the wavelength thick and the light undergoes a phase change at both reflecting surfaces so that the two reflected waves emerge from the film at about a half cycle out of phase.